All right, we're about section 1 here, working through some sample problems. I'm on problem like number 7 example, and I don't even know if the directions say to solve with any particular method, but that's just going to be true for all your homework. You solve it with whichever method you choose, because the answer will be the same regardless. So we have 3 methods for solving a system. You can either graph each one of these lines and look for where they intersect one another visually, or you can use the substitution method, which is solving for one of the 4 variables. And that's kind of handy if you have an easy variable to solve for. Say there's just a 1y or 1x. Substitution method's most handy in that case. And then there's elimination method, or the addition method, sometimes called. And that's what I'm going to do on this number 7. So we want to try to add the equations so that either the x's cancel out or the y's cancel out. Now that won't naturally happen as it stands now. That would be 24 x's and 1 y. So that wouldn't help me solve it. I need something to cancel out. So I have to manipulate the equations by getting a common multiple for either the x's or the y's. And you can do it either way. It does not matter. I'm going to focus on the y's just because they already have opposite signs, and that'll help me. So if I times this first equation through by a 2, you see that'll make that 6y. Then if I times the second equation by 3 times negative 2 would be negative 6, then these would be opposites. I'm perfectly allowed to do that as long as I times it by every term, keeping the balance, and the multiplication would distribute and keep an equivalent equation. So equation 1 times 2, just doubling every term there. We'll see, we get this. Again, completely the same equation, just doubled. Then this equation we're tripling, timesing by 3. Let's see, what is that? 54x minus 6y. And I don't know, 78 times 3. I'm going to have to type that on the calculator. And it says it's 234. Now when I add those 2 equations together, the x's add to 66. The y's cancel out. 30 and 234 is, what is that? 264. Then I can solve by dividing by the 66. And let me type that in. 264 divided by 66 is 4. So x is 4. I need the solution to be an x and a y, the point of intersection, or the point that solves for both x and y in both equations. So now that I know x is 4, I can get y by either plugging in x's here, 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 or here. Any of the 4 previous equations will result in the same answer for y. And you can check that out if you just really have some time to kill, want to see that for sure. But I just picked the easiest equation, whatever looks like it has the smallest number. So I'm going to go with this one. And I'm going to plug in x is 4. So 6 times 4, that makes that 24 plus 3y is 15. Then I have to solve that equation for y. So minus 24. What is 15 minus 24 is negative 9. Divide by 3. Now these don't always have to come out nice and even. You could have a decimal answer or a fraction answer, but just these have been coming out nicely, which I appreciate, but don't think that that has to be that way. So the solution is the x is 4 and the y is negative 3. That should be the number that solves the x for x and y in both equations. Or if they were drawn graphically, that's the point of intersection, the solution to both equations. All right, let's look at another one. Number 8. Number 8 is lined up by x, y's, and constants instead of having the constants on the right side. So if that kind of bothers you, you can throw those constants back over, and that's fine too. We just need these things to be lined up if we're going to use the addition method. And actually, looks like there could be something with a nice solution, a nice crossing crisp point. But that doesn't necessarily always happen. It happens when it's a consistent equation. But sometimes lines are parallel, and I'm thinking this sort of might be something. I notice if I would time this equation by negative 6, I would be able to eliminate the x's, but it also eliminates the y's. So I'm going to lose my variables. But let's just see how that goes. The first equation, I'm going to leave it alone. And then the second equation, I'm timesing through negatives every term by negative 6. So it makes that negative 6x, and notice the negative times negative makes a plus 6y, and negative 6 times negative 12 is positive 36. Now when I add the common terms, that cancels, but so does that. So I lose my ability to have an equation that's solvable. I lose both variables. So I have no variables, and then negative 3 and 36 is 33. So I get this nonsensical statement, 33 equals 0. So it's not solvable for a variable. You see how it's just a false statement. And that means the lines were parallel. When you just get this false statement, that means you had parallel lines, and that's why there's no solution for it. There's no crossing point. And we call that an inconsistent system. And there should be one of them on the multiple choice for this, for a problem like this, when this happens, to say that there is no solution, or the empty set. Something to that effect. And the words that would go along with it if they asked you what type of lines, it would be parallel lines. If we were to graph these two, instead of having a place where they cross one another, they're just going to run parallel. The two lines run parallel. They have the same slope on them, never cross, so no solution. Okay, number 9. All right, now this one, it also looks like something may be up with it. Do you see if I doubled this equation? It's exactly the same as this. So these are the same equation per se. But say I don't notice that. I'm just doing my my process as we've been going through these motions, and I think, well, I'm going to times this by negative 2. So a negative 2 times 3 will make negative 6, and then plus 6, I'll have a nice process where something drops out. So I times through by the negative 2, thinking I'm going to eliminate the x's. But then, if I hadn't noticed it already, I notice it now. When I add it to this second equation, not only do the x's cancel out and the y's, like on the last one, but so do the constants. I get 0 equals 0. Just nothing equals nothing. And it's because the entire equation was equivalent. So it was the same ratio of x's to y's for the slope, but then the y-intercept, the constant, was also the same value. So if we were to draw this, and I don't know what the graph looks like right offhand, but say we drew the graph, then the other graph lies right on top of it. They're just the same line. It's a line with a line on top of it. So we call that a dependent system. And the solution, should be where the two lines cross, where they intersect. Well, they intersect all along that line. So there's infinite intersections, right? The whole line is intersection. So we would say there's infinitely many solutions. And if you wanted to go even further, you could say the solution is x such that x solves this equation, or y in terms of y or x. But the solutions are the things that lie on this line. All right, for the last two examples, we're going to move to equations that have 3 variables. When we have 3 variables, 3 unknowns, it takes 3 equations to solve the system. And what we do to work through these is we create 2 equations in 2 variables. We try to make this look like what we just did. Whittle it down to where you have 2 equations in 2 unknowns. And then we can do what we've been doing over here. So I start by labeling this to kind of help us keep track of what we're doing. So we want to add different combinations of 1 plus 2 equations, or equation 2 plus 3, or 1 plus 3. So we're going to add different combos and thus create what we had before. 2 equations with the same 2 variable. Now you can choose to eliminate the z's or the y's or the x's. It doesn't matter, but just be consistent. So I look at my choices, and really this one's set up where any of the variables would be quite workable. But I think I'm going to choose these z's. They look the most friendly to me at the moment. So I'm going to take equation 1 plus equation 2. And notice if I add 1 and 2 together, I won't even have to manipulate the variables. I can just add straight down 1 and 2 is 3x. Y is 2y. E minus out. 2 plus 8 is 6. So that's a new equation we've created. I'm going to label that equation 4. And I found that again by adding a combo of 1 plus 2. Now I need to create another combination added together to create an XY equation. So I can do what I've been doing over here. And add 2 plus 3 or 1 plus 3. That's really the only combos left. Do you see 2 plus 3 would be handy? 2 plus 3, it's already got the z's opposites there, so I don't even really have to write it down again. I can just look at it. 2x and 1x adds to be 3x. Oh, the y's cancel. That could be a special case. I'm not sure I meant for that to happen. Y and minus y cancels out, and so does the z and minus z, and then 8 and 4 is 12. So maybe this isn't as standard of an example as I wanted it to be, because the standard way to solve it, you want to create two equations that have the same two variables. But this is actually going to be an easier example, because what happens is now I'm able to solve for x and be done with that. I now know x is 4. That doesn't always happen though, so we'll need another example. But x equals 4 would not be helpful to me standalone to just know what one of the variables are, but I have this two variable equation that I can plug x equals 4 into, and then I can figure out y. So I can take from equation 4 and know that 3 times, now that I know x is 4, plus 2y equals 6, that is now solvable for y. And let's see, what is that? Y is negative 3. Now we're trying to get a 3 variable solved for, so we got x, we got y, now we need z. So now I can go up to these larger equations, and I know x plus y plus z has to equal negative 2, or I can plug it in this one or this one. Use any of these big equations, and you know enough now to do that. What's this first equation? We know x is 4. We just learned y is negative 3, and I'm looking for z. So 4 and negative 3 is 1. Throw the 1 across the line, and there we have it. Z is negative 3. And now in order x, y, and z, the x was 4, the y is negative 3, the z is negative 3. And that's called an ordered triple. So we had 3 unknown. Need 3 for that. And know for sure, like on all the others, you can plug that in. Does that x, y, and z work to be this negative 2? If I plug in that x, y, and z, again, you can check it. It should be the one solution where all of these collide or intersect. Now, you might be asking, what kind of figure do we have here? And these are actually planes, 3 dimensions. So they're planes now instead of just a line. And we don't get into graphing that, but there's some visuals in your book if you want to look at that. But that's the one point, kind of a corner point where they intersect. All right, one more example. Maybe this one will be more standard. And it asks us to solve this analytically, and don't let that direction kind of worry you, because we're just going to solve it like we did the last one. Solve it as you can. So I'm going to call this equation 1, 2, and 3. We're going to do just what we did before and try to find the XYZ solution. Okay, so I want to add combos such that something cancels out. On this one, the x's look kind of friendly, so I'm going to deal with the x's. If I add equation 1 plus 3 together, the x's cancel out. So let's just see. X minus x, 0 x's. Y and 6y is 7y. Z and minus 3z is negative 2z. And negative 3 plus the 44 is 41. I'm going to call that equation 4, a new equation we created. Now we need to create another equation that is also missing x. So I'm going to add either 1 and 2 or 2 and 3, a different combination. I'm going to choose 2 plus 3. Equation 2, I'm going to leave it as is. I'm going to write this one down since I'm going to have to do some manipulating. Equation 3, I'm going to times through by 2. I'm going to double everything, making that negative 2x. You know, the signs stay the same if I'm just doubling each term. Now when I add together, there the x's cancel out again and again. You do have to get the same variable canceling out. That's your focus. And this time, not everything cancels like happened to on the last example. I get an equation 5 that has y and z, just like equation 4 has y and z. And then I take those equations, and sometimes it helps to kind of look at them side by side. Now, if you wanted to, all of these numbers are, I could half those, and it'd be equivalent equation. Our numbers a little smaller. I kind of like to do that, and that would be okay to give you easier numbers to work with. So then I take this equation 4 and 5, and I want the z's or the y's to cancel out. I'm going to focus on the z's by timesing by a -1, which will just change all of its signs to -7, +2, -41. Then when I add equation 5 in its form that it already is, the z's will cancel out, and I'll finally be able to solve for a variable. 2y equals, what is that, 10. Divide both sides by 2. Y equals 5. Okay, that's the hard part, getting down to one solution. Then we have to work our way back up and find the other two. So once you know y is 5, you can go into one of your smaller equations. You can't go all the way up here yet, but you can go into either equation 4 or 5, one of its smaller versions. I'm going to take equation 4, 7y minus 2z equals 41, and insert y is 5 that we just discovered. That will help me find z. 35 minus 2z is 41. Bring the 35 over. Let's see. That is, z is +3. So now I know y, I know z, I need to know what x is. So now I can go all the way up here to those original equations. I could use any one of those. The first one looks the most friendly, but any one would give me the same result. We don't know x. What was y? Y was 5. Z is 3. And now we can solve that equation. X plus 8 equals -3. And let's see, y was 5, wasn't it? I'm starting to question that. Yeah, okay. And then throw the 8 over. -11. So now we know the x, y, put in order. X, the y, the z, and double your answer. I'm feeling like I should double check my answer here as well, so you might check me on that and make sure -11, let me just check the first one and show you. -11 plus 3 should equal -3. And let's see, that's -5, -11, 8 basically. Okay, I'm feeling confident in that now. It definitely back in the first. To be sure, you have to check it in all three though. So I encourage you to do that, especially if it's a test. All right, hope that helps.